Hello, my name is Howard and we are from the Fred Hutch Data Science Lab. Our talk will be on the opportunities in the IT and training network related to resources and tools for ethical data handling. We are funded by the ITCR, a program of the National Cancer Institute NCI. In case you did not see the previous talk in the session, the ITN is a network that provides training opportunities for informatics, including a variety of free courses. You can find more about ITN at itcrtraining.org. We aim to help software tool developers make their tools more approachable and to help informatics tool users be more prepared to use scientific software, as well as aware of what informatics tools and resources are available. The tools that we will talk about today relate well to topics discussed in our Ethical Data Handling for Cancer Research course, including the risks of personal identifiable information and personal health information, tips for HIPAA compliance and methods of due identification, cancer data types that are potentially re-identifiable, major methods of data security and practical everyday tips, tips about sharing cancer research data, including relevant repositories, general history of medical research ethics, current and potential concerns for medical research ethics, and strategies to protect and respect research participants. If you are interested in taking this course or checking out our other resources, please take a look at our website. Now we will have a presentation of two ITCR-funded tools for handling clinical data. Presentation on DeepFi, natural language processing tools for cancer research and surveillance. The major goals of DeepFi are to produce rich data models for the cancer domain, extensive natural language processing of cancer-relevant clinical documents, accurate ontology-based summarization of patient phenotypes, simplified processes for cohort identification and powerful visual analytics for cohorts, patients and neoplasms. DeepFi capabilities include document classification, concept and relation discovery, phenotype summarization, patient summarization and store edge, and information visualization. DeepFi identifies cancers and tumors. This table displays scores of a primary cancer attributes: body site and laterality, summary stage, and TNM staging. This table displays scores of the primary tumor attributes, body site and laterality, and diagnosis. Some cancers have additional tumor attributes, such as the bottom 5 for breast cancer. All of the cancer and tumor scores apply to cross-document summarization. DeepFi also discovers attributes for certain concepts, such as medications, radiotherapies and chemotherapies. This table contains DeepFi performance discovering medications and their primary attributes. These scores reflect within document discovered drug concepts and related attributes. Now we will show videos demonstrating two of the graphical tools within the DeepFi application.
Before we do anything else, let's take a minute to look at this interface. First, across the top, we see a toolbar with options to open pipeline configurations, which we call piper files. Open and save parameter files, run the pipeline, or load a help page that will give us additional information about the program. Next, in the left panel, which was automatically populated by the installer, we see the run parameters. First, the input directory containing the patient's documents is specified. Then the output directory for the pipeline output that doesn't get written to the database, such as JSON or HTML files. Next, there are two advanced options that we can ignore for this demo, followed by the URI for the Neo4j database. Finally, the username and the password for Neo4j are specified. Looking at the right side of the screen, we see the piper files. These files define how the pipeline will run. An in-depth look at these files is beyond the scope of this presentation. However, I will scan through one of them just so you can get an idea of what they look like. At the bottom of the interface, we see a log panel that gives us information about the run. Now, let's process the documents. I will do this by pressing the green button in the toolbar. While it is running, at the bottom of the screen, we see the run progressing and logging output. Let's direct our attention back to the top of the interface where we see the status of the run. We can see which patient, patient document, and document number that is currently being processed. When the run completes, we see basic statistics for the run in the log panel. Here we see the total runtime, the number of documents processed, and the average seconds per document. The pop-up dialog indicates that the processing is complete. I will now close this interface to move to the next topic. The next step in our software demonstration will be to run the visualizer to view the results of the documents that we processed. I will now start the visualization tool by clicking on the middle icon. This will launch a web server and a web browser on your local machine, as the visualizer is a web application. As you can see, my button click launched Safari, which opened up the visualizer. The DeepV visualizer is a cohort identification tool that uses the information extracted by the DeepV pipeline and organizes it into a cohort identification workflow. In the first step of the workflow, a user sees a plot summarizing the distribution of patient ages at the time of their first encounter across all cancer stages. A user can interact with this control to refine the cohort by a patient's age at the time of the first encounter. Here, I specify that I only want patients that were younger than 54.5 years old at the age of their first encounter. In the second step of the workflow, the number of patients in each cancer stage is shown in a bar graph. A user can further refine the cohort to a specific cancer stage by clicking on the corresponding bar. Here, I select only patients with cancers that are in stage 2B. The final step in the cohort identification workflow entails reviewing the diagnosis information and biomarker summaries for the cohort. Here we see that of the 3 patients that met my criteria, 2 are diagnosed with invasive ductal breast carcinoma, and 1 has a diagnosis of invasive lobular breast carcinoma. We can also see that DeepV identified biomarkers in every patient in this cohort. And finally, looking at this chart, we see that DeepV found positive ER biomarkers for every patient in the cohort. 2 patients had 2 positive PR biomarkers, and 1 patient had a negative PR biomarker. Finally, we see that only 1 patient had a positive HER2 biomarker, while the other 2 had negative HER2 biomarkers found. Another powerful feature of the DeepV pipeline is the ability to identify and classify specific facts about a patient's cancers. If a user wants to go beyond cohort identification and explore these facts, a user can click on one of the patient IDs in the cohort, which will load a patient detail page, as I will now demonstrate. The first section of the page shows basic information about the patient. The second section shows the details of the cancer and the tumor or tumors. Tumor attributes can be arranged either as a table or as a list. A user can click on one of these values to see the source documents related to that attribute. This will be demonstrated shortly. The next section of the page shows patient documents on a timeline. Clicking on a point in the timeline or clicking one of these cancer attributes that I just mentioned opens a document viewer at the bottom of the page. The document viewer shows the original report text and allows the user to explore information extracted by DeepV. For example, if we wanted to identify the source of the finding, invasive lesion, we click on the term and scroll down to the document viewer. First, we see that DeepV found text related to this finding in 8 records. The text for the highlighted report is shown in the viewer. On the left, we see the relevant terms that DeepV extracted from the report. A user can either click on these terms or use the search box to narrow down the selection. This concludes the demonstration of the DeepV visualizer.
R, or DeepV for Cancer Registries, is a related project. DeepVCR has the major goals of producing, facilitate abstraction of cancers at cancer registries, done through safe web services. In addition to the DeepV major attributes, DeepVCR extracts items such as histologic type, tumor behavior, and tumor grade. The DeepV and DeepVCR team has over 30 members from 10 different sites. Thank you. Please visit our website at deepv.github.io. DeepV is supported by the National Cancer Institute's Information Technology for Cancer Research ITCR initiative. DeepVCR is supported by the National Cancer Institute Surveillance, Epidemiology and End Results SEER program. One of the tools developed by an ITCR member is EMERS, an easy-to-use search engine that lets you quickly and efficiently search through electronic health records. This tool can also help with chart reviews. I'm presenting this information on behalf of David Hanauer and the EMERS team at the University of Michigan, who unfortunately couldn't join us here. However, they can be reached on Twitter, through the EMERS website, and by email. If you're interested in learning more or using EMERS in your system, please don't hesitate to reach out to them. Before I begin, I do need to mention that funding for eMERS has come from the NIH through the ITCR and National Centre for Advancing Translational Sciences initiatives. Additionally, there is a small license fee paid to the University of Michigan for part of the eMERS toolkit, although this fee is waived for academic use within eMERS. If you've ever worked with electronic health records, you've seen that information can be stored as text in the form of chart notes, which is unstructured, as well as in table or list form, which is generally structured. An estimated 80% of the data you can pull from EHR exists in the unstructured free text notes. That's a lot of information that is potentially useful for clinical research, but it can be challenging to extract this type of data. Many, if not most, medical centres don't have self-service tools to explore the data within the unstructured free text. Researchers interested in using EHR have to wait for a specialist to go through the records and pull the information they need. This can be both tedious and time-consuming. eMERS was developed as a painless way for researchers to extract information from the unstructured data that makes up the majority of EHR. It is an information retrieval tool that can handle free text data from all types of medical specialties and domains, allowing you to easily find records that match your criteria. Searching like this is an effective way to fulfill many kinds of use cases requiring EHR data. eMERS has a point-and-click interface so users can quickly get started. It does not require any programming knowledge to use, making it a great choice for non-technical researchers. It can also search across all notes and multiple patients at once. eMERS is open source, free to use, and is accessible from any modern web browser. However, it does require a dedicated clinical IT team to install and securely manage the system. eMERS allows you to find cohorts based on things mentioned in the notes, like diseases, drugs, symptoms, or anything else that might be mentioned. You can create lists of patients who might be eligible for a cohort in a couple of minutes. Each list can contain up to 100,000 patients, and there is no limit to how many lists you can have. Lists can easily be changed by deleting patients or adding new ones. You can share the list with your study team, and even annotate the patients by tagging them and adding comments. These tags and comments can be exported, along with the patient lists, to a password-protected Excel file. A patient list tool in eMERS allows for the creation of temporary lists of patients, perfect for reviews preparatory to research where patient information is not meant to be saved. eMERS is especially useful for finding rare things in huge numbers of patient records and has been successfully used to create cohorts for rare cancer types. You can find out more information about these efforts in a recorded talk at this Vimeo link, which can also be found on the eMERS website. Once you've identified patients who might be eligible for your study, eMERS will also quickly take you to the part of the EHR that contains the information you searched for. eMERS will highlight your search terms within the electronic health records. Chart review becomes quick and easy. Each search term can be highlighted a different color. You can even customize the specific colors you use for each term, so you can group concepts and terms by color for faster recognition. You can also expand your search terms using the synonyms option on eMERS. For example, in the search on the screen, you're interested in identifying patients whose records mention shortness of breath. In addition to this term, eMERS will search for 28 other terms used to describe the same symptom, as well as 30 additional spelling alternatives to your query term and the identified synonyms. Your search can include acronyms, abbreviations, professional and consumer terms with spellings, trade and generic drug names, species, chemo regimens, phrase variations, malapropisms, idioms, neologisms, organizations, companies, and more. eMERS also has the capability to search in multiple languages. eMERS has been installed in a number of hospitals and research labs, including multiple US locations as well as some newer installations in Europe and Asia. It is vendor agnostic and can work with data from any kind of EHR. If you are interested in learning more about eMERS, you can check it out at the project website project-emers.org, or you can contact the eMERS team at the University of Michigan using the email address emers-team@umich.edu.